Okay, thank you. So yeah, I'm going to talk about towards a theory of mind for artificial intelligence agents. And theory of mind defined by Premack and Woodruff is the ability to impute mental states on others. Don't mistake that for animacy. Animacy is the ability to tell if something even has internal states, okay? They're related concepts, but they're not identical. There. All of this started, I guess, ALIFE2023. We had a workshop or panel discussion about artificial intelligence, and then my collaborator, Chris Adami, was talking about information theory, mental representations, and how all of that amounts to general purpose artificial intelligence. Was a very cool discussion. And I pretty much wrote up the core idea as a blog post for the conversation and said, understanding the 4 types of artificial intelligence through the light of information theory. Not knowing that this became a thing. So if you Google 4 types of intelligence, you pretty much get my blog post or a derivative of this. It's actually in Wikipedia under 7 types of intelligence. And even our future overlords know about it. I mean, as ChatGPT, and it tells you this theory back. Curiously, ChatGPT understands that I wrote it. That's kind of cool. Most people don't cite me because, well, it's a blog post, right? And a blog post is just an opinion. That's kind of the shortcoming of all of this. It's consistent and nice, but just an opinion. Anyway, let's revisit this idea for a second and talk through the 4 types of intelligence. I mean, the first type of intelligence is pretty much one that is a purely reactive machine that just responds to stimuli. An artificial neural network that has no hidden states is pretty much an example of that. It knows nothing. I mean, it performs perfectly, not fine, but it remembers nothing. That's what I mean. And information of this thing is 0. Quite easy to compute. And then, of course, you extend this to limited memory machines, recurrent neural networks, things that have states. And these machines can actually know something about the environment, or but I say remember something about the environment. And curiously, we did quite a lot of work on representations, quantifying this with information theory, finding out the nodes that do that, and so forth. So the second step, where we're on the way. And then if you extend this, the moment there are things in the environment, some of those things have hidden states, and you want to actually understand those hidden states, and that means that you have to extend this thing to theory of mind, understanding that things have hidden, knowing these hidden states. So it's pretty much like, I know that you know type of thing. Strange enough, Chris and I, or our labs, did nothing on this. We just ignored this point because we more or less were more fascinated by the last extension of this, which are self-representations. Sort of, I know, therefore I am, or I know that I know. That's kind of the highest level of information that you can about yourself. And we worked a lot on this in phi theory, integrated information, lots of things. It's really difficult to explain and not the point. The point is that there's this gap in there. And then my collaborator, Jory, Schossau, and I decided, okay, because if there's this lag, let's fill this void, right? Let's go there. My clicker doesn't really work. There's a lot of other work on this, okay? And I mean, particularly in cognitive science, psychology, and so forth, but we're talking about machines. So in that computer science domain, a lot of people try to use AI to pretty much predict internal states. There is somebody who wants a coffee, and that obviously means that that person is tired, okay? We heard talks about this already. It's really important in reinforcement learning of groups of agents, because if you want to get them to do stuff together, they have to understand who does what and understand that they have internal states. We were not so much interested in that, but interested in quantifying how much information my hidden states have about your hidden states. And once we have that, identify which nodes in your brain do that for you. So you have to construct an experiment in which you prove that these agents that you're dealing with actually do have theory of mind. And it starts with a perception phase, or they could make up their mind, but we pretty much tell them what they should remember, and that has to happen in separate places. So you have 2 agents, you tell one agent something and tell another agent something, and they cannot observe each other. Otherwise, they wouldn't impute the states from the agent, they impute the states just from the environments. They have to be separate. And then we call this a communication phase. They have to kind of talk with each other or do something that allows them to observe each other to impute those hidden states. So communication phase. And then we separate them again because we now inquiry them if they still remember what we told them in the beginning. And then we also ask them if they know what we told the other agent. And they also have to be separate because otherwise they just repeat the answer of the other agent and then they never had that again, just from the environment. The environment looks like this. We have 5 rooms, a top room where the top agent starts, the bottom room where the bottom agent starts, and they have to run into always the right room. So the bottom agent runs in the room on the right, the top agent runs in the room on the left. For this agent, the room on the right. And the top floor and the bottom floor are color-coded, red, blue, or green. They have to remember this color, and they have to run into these extra rooms on the sides and press the lever of the color of the other agent. And while they're doing this, they have to tell us the color of their own room. In theory, you can just cheat. You just run up, look at the room of the other agent, and then go to your room and never talk to this guy. So there are these doors, and these doors fall shut the moment the first agent goes through this. So if you start doing this little puzzle in your head, you realize that you cannot cheat in this environment, right? In the middle of the room, in the middle room, we actually allow agents to talk or exchange information with each other. And that works like this. You have a couple of sensor nodes that tell you what is in front of you, what color the thing is that is in front of you, and you have two binary sensors that allow you to hear beeping, let's say. Obviously, the other agent, both agents also have actuators. They can turn left, turn right, move forward, do nothing. When they run into a lever, that's when they make their choice of pressing this lever. And then they also have these two beep modes, which basically allows them to utter the color that they're thinking they have. So this agent, for example, runs over the other into the other room, says nothing the entire time, doesn't beep at the end, but presses the green lever. That's correct, because the green lever is the color of the agent on the bottom. At the same time, it doesn't beep, so it only gets partial credits for only knowing the state of the other agent. Or maybe the agent guessed it, who knows. The other agent does this much smarter. It just says green, 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 green while it runs to the other side, which is exactly the correct answer because it has to say green at the end. That's probably where the first agent got the idea from, that the other agent was from a green room. But at the same time, it completely missed its own lever, so it only gets partial credit. So you only get 1 point in total if you get all 4 cases right. Okay, we run a genetic algorithm to optimize brains, neural networks to do this. We have population size of 100. We have each agent is cloned at the beginning. So one controller is controlling the top agent, independent copy of this brain is controlling the bottom agent. And we evaluate them as pairs. Each agent is tested on all possible combinations of colors, so 3 by 3, and then we test them twice just to have more statistics, which takes quite a lot of time. We use recurrent neural networks. You know them. We know Markov brains. I hope you know what they are. They're pretty much sparse neural networks, which use probabilistic, deterministic, and all computational functions from genetic programming. They're really nicely involved in our toy model, so to speak. We maxed out our high-performance compute centers capabilities because it needs 1 million generations for Markov brains to evolve this task. And of the 500 replicates that we used, only 34 of them went to perfect performance. This seems to be a really difficult task for them. Recurrent neural networks are harder to evaluate because there's more computation. So we could only run this to 500,000 generations, and we got 1 perfect performer and 8 near perfect performer. These eight get 1 of those tasks wrong in 1 of those 18 combinations. So they're really near perfect performance. Over time, you see this is the fitness plot where over generations, you see the performance increasing for all the perfect performers. It's not that informative. But what we thought is, as you showed you in the beginning, the only thing you have to do is you run in the middle room, you scream your original color, and then you press the color that you're already screaming. You keep screaming that color, because in the end, you have to actually report this properly. So this is what we expected every agent does. We tested every of our 40 agents with all of the other 39 agents. None of them actually could talk with each other. They like no possible combinations. They got, I think, 65% best in one of the cases. Why? What's going on here? And I have no explanation why that is, but they're kind of singing songs to each other. Blue, 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 green means I came from a red room. Or red, blue, green, green, blue means I came from a green room. They make up a song. Sorry, I don't know why they do that. That perfectly works when they meet the correct agent that is preset to do this, but they're not intuitively saying what we thought they do. I find this quite curious. Okay, but let's measure the whole thing now. We want to still quantify all of this. And if you quantify this with information theory, you have random variables, you express random variables as Venn diagrams. So we want to actually measure the brain states of the source agent. That's the one that has the theory of mind about the other agent. That's the target agent. So we have another circle. That's the random variables for the brain states of the target agent. And then you have the states of the environment, because you need to have some kind of ground truth that tells you that you're measuring the correct thing. So the environment in this particular case tells the top agent here it's supposed to be green. So there's information in the environmental states that is then shared with the brain states of the target agent. So now the target agent knows where it's supposed to go. This target agent, these areas here is stuff that the agent just makes up in their mind. It's not coming from the environment, that information is just basic start states, rests of computations, random numbers, doesn't matter. The target agent now has to run in the middle room and say something, and that means that it has to share the information with the environment again. The source agent needs to hear this, and the source agent now shares the information with the target agent, and it's actual information that's important, and that's why it's also shared with the environmental variable. So that happens through communication, as I said this before. And this little square in the middle is the information that we're measuring, that a source knows that target knows something about the environment. That's the information theoretic quantity, the joint information. To give you another example, if I make up a number 7 and you expect to know this number, you can fall into the trap to say, I just share this information with you, right? This is information that's shared between my brain and your brain that never went through the environment. Well, that's called telepathy. We don't study that, okay? So if you really want to get me to have this information, you have to share it with the environment. And the moment you share this with the environment, we can share it all together, and then I know it. That doesn't have to be this exact number. I don't have to share 7 with you. I can actually share 7 beeps with you. And then you internalize that, you perform some kind of computation on this, assemble the correct answer 7, and then suddenly you have the information that is shared between all of us. Yes. So where is the information stored? So we have a red agent on the left and the blue agent on the left, on the right, and we tell one agent, you are red, and it stores the information in 2 nodes. So this agent now knows I'm red. The other agent now knows I'm green in another set of nodes, sort of states in the environment, states in the neural network. Now, if the first agent now gets the information that the other agent is green, it has to put this in other nodes, otherwise it would confound this. So that's the same for the other agent, so both agents now know what's going on. If we measure one information, we're measuring the information between these states. If we measure that for the other agent, well, then we measure the information in the red states. So measuring the theory of mind for one agent is not automatically the theory of mind for the other agent. This is 2 separate concepts. Now that we can do this, can we ask where these nodes are? I mean, we know that they have the information because they're perfect performers, but can we localize this information? Well, the way we do this is we actually test all possible tests of all possible sizes and identify the set that has the most information about the theory of mind, which, I mean, if you think about this, is a very, very, very large number of sets that we have to test. Fortunately, there is the greedy algorithm. We just published this in a different paper, which allows us to identify these nodes in such a way that we eliminate the node with the least information, eliminate the next node with the least information, eliminate the next node with the least information until the information plummets. Because the moment the information plummets, you identify the essential set of nodes that contains the information. If the set is very small, this red line looks like that. If the set is very large, the red line looks like that. Now, we did this for Markov brains and for recurrent neural networks, and in Markov brains, it's pretty much meeting our expectation. You remove nodes until suddenly you find a small set, and then information plummets. For recurrent neural networks, that doesn't look like that. It didn't surprise us because in neural networks, we know that information is distributed or smeared because everything is connected with everything, and the entire neural network is doing the entire computation. And that's why you cannot really remove a single node because they're all involved in this process. That works much better in these more sparse Markov brains. But did we actually identify the correct nodes? So we just measure something and identify nodes, but are they the right ones? So we rerun the experiment, and every time an agent actually goes into the final room, we put noise in those nodes that we identified. If the nodes that we identified are the theory of mind nodes, they should still be able to get their own color right, but they should not be able to get the color of the other one correct. And this is exactly what you see there. The performance that you have on your own room color is the red performance, and you see that it's much better than the performance that you have on the theory of mind or the other agent's color. That's the black line. That works for Markov brains quite well. again, that doesn't work for recurrent neural networks. First of all, because if you do random numbers into states, you mess up their performance much more significantly than in Markov brains. And secondly, again, because of the distributed representations in recurrent neural networks, it doesn't matter which of those nodes you hit, you pretty much destroy the entire thing. So unfortunately, that didn't work for recurrent neural networks, but in Markov brains quite nicely. So in summary, we suggest an information theoretic function which quantifies the amount of information that the source agent has about the target agent's representations of the world. Okay. Together with the greedy algorithm, you can identify the theory of mind nodes, which are essentially carrying that information. We confirmed what we already know, that Markov brains aren't recurrent neural networks. Okay, fine. This is not the end of it, because there's a couple of things that are incomplete here, particularly the case where we observe each other and you still have theory of mind. So if I see you drink a coffee, I infer from that that you are tired. But do I know this from you being tired and you communicating this to me? Or do I see that from the environment? If you really want to resolve those cases, which in our particular experiment don't show up because we constructed the experiment, that's not a problem, well, then you have to do a much more complicated Venn diagram, which extracts the sensor information that we have about the environment and so forth. And it's really, really complicated to solve. So that's something that I hope we can do in the future at some point. Thank you so much. And of course, everything was done with Mate